This is the last in the set of videos about how to graph these various polar functions. So we had looked at basic polar coordinates. We had graphed a cardioid, we had graphed a rose, we had graphed a Lime Mason. That was a thing that looked like a little lima bean in the middle. We've got one more to graph by hand, then a couple that I want to show you that can be done on a computer, which are kind of cool. So let's take a look at this one. This one's a little different. I got an r squared equals 5 times the cosine of 2 theta. Remember, we were doing these by coming up with the equivalent that was in rectangular form. So let's try this, except we'll take the square root of both sides, and we'll look at y equals the square root of 5 times the cosine of 2x. Now, there is a little bit of hand-waving involved in this, in the sense that I'm not taking the square root of the 2x either, but cosine only goes between -1 and 1. So if I take the square root of 1, I'm still going to end up with a 1. It's the other part that we'll worry about in just a little bit. So when I make a little sketch of this, some of this is going to look very familiar, right? The cosine function starts up at the top. It goes down and comes back up again on the interval from 0 to 2 pi, except that this one now starts with the square root of 5 up there and negative square root of 5 down there. That 2 that's in front of the x is going to change my period. So instead of it going from 0 to 2 pi, it's going to go from 0 to pi. That's a pi over 2. That's a pi over 4. That's a 3 pi over 4. And then, of course, it repeats again from pi to 2 pi. So what is this thing doing? This thing is the square root of 5 when theta equals 0. And then the radius decreases to 0 on the interval from 0 to pi over 4. Now we've got a little issue. And that is, look at this piece on the bottom here from pi over 4 to 3 pi over 4. Really, this thing doesn't exist because the original equation has an r squared in it, right? So when can r squared be equal to a negative number? It can't. So this graph actually stops between pi over 4 and 3 pi over 4. It just doesn't exist. And then it picks up again on the other side, and then it increases to the square root of 5 on the interval from 3 pi over 4 to pi. Now, just like that other graph we did, that rose that repeated itself, this thing's going to do the same thing. So it's going to increase to the square root of 5, then it's going to decrease to 0 between pi and 5 pi over 4. There's going to be a break in it between 5 pi over 4 and 7 pi over 4, because again, you're going to run into that issue where you've got part of the graph below the axis, and that doesn't exist. So here at 7 pi over 4, it'll pick up again, and it'll increase until it gets to 2 pi. So what does that look like when I go to graph it? Well, here's what it looks like. I've got a radius of the square root of 5 when theta is equal to 0, and then it decreases to 0 by the time it gets to pi over 4. So this thing has a little asymptote here at pi over 4. And then we said between pi over 4 and 3 pi over 4, the function simply doesn't exist. It picks up on the other side and goes to square root of 5 in the direction of pi. So here is the square root of 5 in the direction of pi. We get negative square root of 5. Then we come back up to the top. We said between pi and 5 pi over 4, it goes back to 0. Okay. And then those asymptotes take over, right? Between 5 pi over 4 here and 7 pi over 4 there, the graph doesn't exist. And then it picks up here at the pole and works its way back to the square root of 5 by the time you get to 2 pi. So what is this thing? Well, there is a name for this thing. It looks like the infinity symbol, but it's actually called a lemniscate. Okay, where in the world did they come up with the word lemniscate? Lemniscate is an ancient word that means to decorate with ribbons. So it's supposed to look like you're decorating with ribbons, and of course, now that I say that, yeah, all right, maybe I could see that I'm decorating with ribbons. But that's what a lemniscate is. And a lemniscate's kind of unique in the sense that it's not given in terms of r, it's given in terms of r squared. And because of that, there will be certain places on this graph where the function simply doesn't exist because you can't have r squared equal to negative numbers. So there is a way still to do it by looking at the original graph. You just need to know, in this case, where the graph exists and where it doesn't exist. All right, let's take a look at 2 other graphs. We're going to take a look at the graph of r equals 1 plus 2 theta, and we're going to take a look at the graph of r equals the log of theta, the common log of theta. Both of those I'm going to graph on Desmos. There are names for each of these things. This first one is called the Archimedes Spiral, named after Archimedes. And this one down here is called the logarithmic spiral. All right, so both of those I'm going to graph using technology because this is not something that you would graph by hand. On Desmos, I can graph thetas, or input thetas, I should say, by typing the word theta. So r equals 1 plus 2 theta would be done by r equals 1 plus 2 theta. Okay. So if you look at my graph, this one, they automatically set it to go from 0 to 12 pi. Is that a good window? Let's see. If I zoom out a little bit, I get more spirals. And if I zoom out more and more, I get more and more spirals. Now, on the theta interval between 0 and 12 pi, I create a set of spirals that looks like that, and it stops here at 12 pi. Now, if I want more, just put in more values of theta, and this thing will keep going and going and going. So there's your Archimedes spiral. Now, let's take that out for a second, and I'm going to graph the second one. R equals log theta. Now, on the window that I had set up for the Archimedes spiral, that log theta doesn't look like much. So I'm going to zoom in and zoom in, and zoom in and zoom in. And all of a sudden, I get this graph that gets closer and closer to each other because I'm taking logs of numbers, right? So I'm taking logs of values that are close to 0. Logs of values that are close to 0 are very negative. So you see it comes on this side over here and then spins around and around and around and gets closer and closer until it just ends because 12 pi was the default. Okay. Would it be possible to put in negative values for the log function? No, because if I put in negative values, I can't take logs of negative numbers. Logs can produce negative numbers, but I can't take logs of negative numbers. Okay, so in this case, this is what I get from my logarithmic spiral. And if I want more values, I want to see this just keep going and going. Now they're going to start getting closer and closer and closer to each other because when you take logs of numbers, that compresses them. All right, let me go back to my Archimedes spiral for a second. Right, for this one, I'm going to have to pull the window out. We looked at the logarithmic spiral and we said, nope, we're not going to put any negative values in for the logarithmic spiral. That wouldn't make sense. Can we put negative values in for the Archimedes spiral? Well, right now I have it set to go from 0 to 12 pi. What if I went from negative 12 pi to 12 pi? Oh, look at that. By only including the positive values in there, I lost the other half of my spiral. So what if I decide to graph this as two separate graphs? So what I'm going to do is, I'll move this over so you can see what I'm typing in here. I'm going to leave the r equals 1 plus 2 theta, and I'm going to set that to go from 0 to 12 pi. And then down here, I'm going to put in an r equals 1 plus 2 theta. Except I'm going to make this go from negative 12 pi to 0. And now, I have a graph in Christmas colors. So that's the graph that's the negatives, right? That's the graph that goes from negative 12 pi to 0. That's the Archimedes spiral that goes from 0 to 12 pi. Now, if I combine them, you can see what I'm missing by only including half of the values in there. And where does this turn over? It turns over right there at the origin. So, well, not there at the origin. I should say over here at 1. Because that red graph starts with theta equals 0. 2 times 0 plus 1 is 1. On the other hand, 1 plus 2 theta, again at 0, still produces a 1. So they meet here when theta is equal to 0, and that radius is equal to 1. And you can see how they interact with each other. Okay, so there's the Archimedes spiral, the entire Archimedes spiral. Well, at least apart from negative 12 pi to 12 pi. The point being, don't leave out negatives because in some cases it produces values. All right, and that's the end of the polar graphs.